Okay, so this is an intro to programming thinking, and before I get started, I want to talk about the Arduino itself as a piece of hardware first. So what is the Arduino? The Arduino is a microcontroller which uses C++ code to perform actions and control components. So it is literally just a small controller of operations. It's basically a tiny computer. The Arduino itself is a piece of hardware which can direct and receive current through these different pins. And so the digital pins are right here on this left side, and that's where we get and send our information. So when we use these with input and output devices, we can actually interact with the outside world. So we can take measurements, or we can move a motor, or we can light up a light, that kind of stuff. So this project will be using input only though, so we'll be focusing on reading info rather than we would be on sending commands to outputs or to motors or whatever. So here's a generalized breakdown of how we want the Arduino to interact with our code and with the input devices. So our code is what I would consider the mind of our Arduino. It tells the Arduino how the senses are hooked up to the brain, how to read those signals to the brain, and what to do with those signals. So the mind is the decision maker, it controls the flow of logic, and it's what actually converts numbers or otherwise into your electrical signals. Those electrical signals travel through our brain and nervous system. So the decisions made in the mind get sent to the pins, and these are wired to the senses. So the brain and nervous system is our pass-through, and this is the actual physical Arduino. The brain and nervous system is also where you would send a request to fetch a readout from the senses so that you can actually figure out what is the current value of one of my sensors, how is it working, that kind of thing. So the brain and nervous system communicates directly through wiring to our senses. The senses themselves interact with the outside world to gather information as an electrical signal. And I'm saying senses because we don't include any output devices. So these are all sensors, which are just taking in information. So then, once they've taken in this information, they send the output, which is carried back through the brain to the mind, where it is interpreted and stored. And then based on that information that we just got from the senses, we can do it all over again. The mind can make some kind of decision to send a signal to receive more data or not to through the brain and nervous system. And so we keep going through the cycle, and we keep storing data as we go through the cycle. So the key to this cycle is that in our bodies, we're only aware of the connection between the senses and the mind, where we get our feedback and it comes directly to us. We don't have to think about, okay, how is my brain wired through my brainstem to my eyes, and how do I have to set that up every single time I use it? All of that is not in our consciousness, and so it's not something we have to think about when we're setting stuff up. When we're using the Arduino, though, we actually do have to declare, okay, my eyes are wired to this pin, which I have to fetch in this way, and I have to do this explicitly. So when we're writing good code, we have to do every single step explicitly, and it's often very easy to forget that we have to do that. Okay. So what does this mean in terms of what we're going to be seeing in front of us on Wednesday when we get the kits? This is the brain, mind, body breakdown. So we have our pins, this is where we send our signals. This is like our nervous system. We have wires, which connect to the sensors. We have both of our eyes. This is our sensing. And we have the brain. The brain is the Arduino. And we have the mind. The mind is our code that we compile onto the board, and then it can make decisions on the brain, which is the Arduino. So you can see here that we have to wire it to power. So these pins on the bottom side, they're just constant power. They allow the device to just operate generally. And then the two middle ones, the two middle wires, they are connected to the digital pins, and the digital pins are where we get the actual readout. So this is where we're getting our information from, and this is what we're going to send from the brain into the mind to make decisions with. So the ultrasonic sensor. These are the eyes of our device, and they're cool because they don't actually use any light at all. The ultrasonic sensor has a sound emitter, which is called a trigger, which sends out a sound wave. This sound wave then bounces back and is received by the echo. So even though what looks like two eyes on this, one of them is just an output eye and the other one is an input eye, which is kind of bizarre when you think about it. But one of them is basically constantly listening and the other one is constantly putting out sound waves. So based on the time it takes from the trigger, where it outputs a sound wave, for it to return to the echo, we can tell up to about 3 meters how far away is the object that I bounced it off of. In addition to that, so the ultrasonic sensor for the most part sees straight ahead of it, but it also has a viewing angle of 15 degrees in all dimensions. So this forms a cone. But it can't tell you where in the viewing angle, so where in that cone the object is, only the distance perpendicular to the sensor. So I couldn't tell you with the sensor if you were to the left or to the right of me, but I can tell you that you are 100 millimeters away from me. So what is a viewing angle actually physically? The viewing angle is a projected cone from the center of the device that is all of where it's visible, and so you can see it the wider the further you get away. But when someone is passing through your viewing angle, I will just read a constant distance. I can't tell you whether you are just entering or whether you're just exiting my viewing angle. However, if, for example, someone were to walk like this towards the sensor, then I could tell you there's a varying distance and this is the direction you're going in. But because you can't place these sensors in the actual doorway, they have to be perpendicular to the doorway, and so the person's path is going to be perpendicular to the viewing angle, like the first one that we saw. And so what that means is that we can't tell from just one sensor what the direction of the person is who is entering or exiting the room. So I don't know, I have to guess. So the solution to that is that we can use two. When we use two side by side, parallel to the path of the person entering or exiting the room, we have something to compare to. So let's take a look at what happens when one person passes through. You can see when this happens that one of our sensors is going to get a hit first, and then the second one will get a hit. So if we know that we're listening on both, and all of a sudden on only one we start to get a hit, we can tell what the direction of that person was based on which sensor they hit first. Likewise, if someone is exiting the room, they would hit the other sensor first, and so we have to listen for that one as well. Okay? So, depending on which direction the person is headed, one of the sensors will notice them first, and then we can decide in our code which one indicates an exit and which one indicates an entrance. At least that gives us a baseline to compare to now, compared to just one, where we can just say, okay, they're 100 meters away, or 100 millimeters away. So, this is nice. We have our two sensors and a basic understanding of them, and those will be plugged into the Arduino, and we'll decide what pins later on. But in order to actually decide and keep track of which one's actually getting hit first, we have to write code, and before we can do that, we have to write an algorithm. An algorithm is a set of instructions, or logic, which are decision makers. Just making sure I'm still recording. These are not actually written in our coding language, C++, because we want to use algorithms to make sure that our logic is sound in English before we can translate it to code that the Arduino can understand. So basically we're writing a thought map or a flowchart or whatever you want to think of it as. And then, once we are confident that this is all correct structurally and that all of our variables are carrying through, every decision that we're making in our code makes sense, then we can actually translate it into the actual language that the Arduino will understand. And the benefit to this is, if we run into any errors when we're actually creating our code, we know that those errors, for the most part, are going to come from syntax errors. So syntax errors is like you're making a typo, or you've accidentally named your variable the wrong thing and it's getting confused, or stuff that is fairly simple to remedy because it's just we look through the code very thoroughly, we find that you're missing a semicolon. It means that we can actually proofread our logic before we move on to translating. So when we're writing these flowcharts and we're writing these algorithms, we need to have a couple of building blocks so that we understand what's in our repertoire. So there are two logical building blocks, and those are loops and conditions. Loops and conditions are what tell your code what to do next. That's where you can say, if this, then that, or while this is happening, then do this. And then the bottom four blocks are actions. So we have declaration, we have variables, which themselves aren't an action, but the editing of a variable is a very common action. And we have inputs and outputs. And so what we would do is we would use these four blocks, declaration, variables, input, and output, and link them together in the appropriate order using loops and conditions. So let's look in more detail at what each of these mean. So let's talk about declarations. Declarations are basically that we're indicating where any of our inputs and outputs are wired to. So we just say that there is something wired to digital pin 9, and this is where I'm going to be wanting to read out from there. So, for example, I would declare an ultrasonic sensor at pins 8 and 9 because I need to have the echo and trigger. And we'll also, in declarations, declare what packages, and packages are other people's code, that we want to import to be using in our own. So we'll talk about this later, but this would all happen at the setup of your code. So what would happen before you would enter any loop logic, because you only want this to happen once. So the next building block is a variable. These are where you keep the information that you've collected as your code is running. And so it's very helpful because you want to be able to store this and then read it again and then modify it, and then you can make decisions based on the value of any of your variables. So like we're setting up with declarations, we have to create the variable at the beginning of our code. So we would create some empty variable, favorite color or whatever. You can name it however you like, as long as you keep track of it, and it's not too long usually. And then once we have created it, we can update it. We can add some value to it. We can read it, or we can just modify it in any way. We can use it for calculation, and it's helpful for that because that allows us to make decisions. So the variables can usually store numbers, letters, or booleans. A boolean is a true or false value. We may or may not get to use those. It's helpful to know what you can use in a variable. Okay, an input is information that we have to ask for in our code. Input is some kind of information that is flowing from somewhere, and we have to request it, and then we can do something with it. The input can come from anywhere, but in most code it comes from the person using the code, but in Arduino code, often it comes from the sensors. So our project will only take input from the ultrasonic sensors, but my example uses input from a user. So when we're ready for an input, we have to fetch it. So I would say fetch input from user. But what that does is that assigns the value of that line to whatever the input from the user is. But it's assigned that value, and then we just move forward. But what we actually want to do is we want to save it to a variable where we can save it and access it later and modify it. The line where we fetch the code then should be set equal to whatever we want the name of the variable to be. Okay, so I would say favorite color is equal to fetch input from user. So what this means is that if we want to check the user input again to update favorite color to see has it changed, we have to run this line again. So this is useful to know because when you're doing a loop, you would know that you want to include favorite color at the right place in your loop, so that you update it whenever you need a new update. So we always have to run this line again to update the value of our favorite color. So this is all nice, but so far we can't make any decisions with this. So what we want to use is a conditional. A conditional is a line where you check something, you check the value of something, you check and see if it's true, and then you're able to direct your code to do or not to do something based on how that conditional ends up checking out. The most common conditional is an if statement. It's the easiest to use. It just uses one condition, and it's very simple. The if statement operates on any condition. So if my favorite color is equal to blue, this is an if statement. I usually put my conditions in parentheses because that's common syntax for C++, and so when we're writing our algorithms, it's helpful to just have that. And so if the condition of true is true, I want to be able to actually do something. And so I would execute what I would call a process. So the process should be found inside of my curly brackets. So in this example, I would say, if my favorite color is equal to blue, if what's in the parentheses ends up being true, then I would add 1 to the people who like blue counter. So then I would just increase the number of people that I'm storing who like blue. Right? So that's my action based on the condition being true. If my condition is false, I would just skip whatever is in these curly brackets and I would just keep moving in the code, whatever's next. So when we're doing our code, we can actually write if conditions one after the other to check for multiple different cases. So I can say if it's blue, then do this. If it's green, then do that. If it's red, then do whatever, etc. And that's nice because it's specific. There is such a thing as an else condition, but it's too broad, and what ends up happening is a case that we don't think of ends up being included in an else statement, and then we get our code terminating by accident, or we get it confused, and that's not actually where we want it to go. So it's best to write multiple if statements until you get comfortable with the idea of using conditionals. So what this allows us to do is it allows us to perform different processes based on what our conditions end up being. So finally, we can also make our condition depend on multiple different variable values or conditions, and we can link them together with an and or an or. So I can say if the value of my favorite color is blue, or if the value is aqua, then I can do the same thing based on whether it's one of those, because I want to lump those together. Or if I wanted my favorite color to be blue and I wanted my name to start with the letter F, then I would use the and to link those together to make sure that both of those have to be true before I can proceed to do the process within the brackets. Okay. So once we have we have inputs, we collect them, we save them into variables, we use a conditional to decide whether we're doing something with it, and then what we want to do is we want to create an output. An output is something that's useful, and that's usually what most code has as its intention. And so in our project, the only time we will be using an output is when we save information to the Arduino hard drive. This is called the EEPROM, and we'll be talking about this later, but we'll be saving to it basically. We'll be saving numbers to it. Another common output method is to print to the computer screen. And so that's usually used in user interfacing code, which we're not writing, but this is the example. So usually we're outputting the value of a variable. So for example, in this case, I would write print, and then I would print the string, the number of people who like blue is, and then I would print the variable, the people who like blue counter. And that tells the user in a useful way how many people like the color blue. And that's an output, and it ends up being useful. Okay. So a loop. A loop is what allows us to do all of this, do it once, and then do it all over again. So if in drawing your flowchart, you draw an arrow that climbs back up to a certain step and says repeat from here, and climb down again, then you've created a loop. The physical loop in your flowchart, and it's called a loop in code as well. Loops can be conditional, like a while loop. So while something is true, then do something else. So for example, while the user input is not equal to stop, then keep doing these steps. So the way that it runs through is it checks the condition, it does each step, it reaches the end of those steps, and then it checks the condition again. And if the condition is false, it will stop, it'll just exit this curly bracket, and it'll do whatever's next in the code outside of those curly brackets. If the condition is always true, it'll keep executing what's in the curly brackets over and over and over again. And that's to infinity, if nothing changes whether the condition is true. The other type of loop is a counted loop. So in a counted loop, regardless of what changes of our condition, will always have an end to it because we've decided, okay, I only want this to run 9 times or 10 times. So the way that we do this is we use an index and we count how many times it has already repeated these steps. So in our condition, which is these parentheses, we tell it where to start the index, when to stop the index, and how much to increase the index each time it completes the steps once. So for I starts at 1, up until I is less than 10, increase I by 1 every time you finish what's in the brackets. So you keep checking this. So then what this code would do is it would run the steps in the brackets 9 times over, and then it would reach 10, and then it would be done. And then it would exit, and it would just keep going whatever's in the code. So now that we have these building blocks, we have conditionals, we have loops, and we have actions. We want to write conditions in circles because we want to distinguish those from our actions, because we want to be able to see, okay, this is a circle. It should have 2 arrows coming off of it. There should be 1 arrow for if the condition is satisfied, then we do what's in the brackets, and then it goes off to another box. And if the condition is not satisfied, then we have an arrow of a different color that goes off in a different direction based on the condition being false. So it usually helps to color code these so that we can actually distinguish what's going on, and you can see that in this flowchart over here. We have, is the sky blue? If yes, then print all good. Sorry. And if not, then print or ask the user if they want to proceed, store to continue, whatever. We skip the one that it's only available if the condition is true. And so we write actions in boxes, and so that's printing something or doing something or updating something or asking the user. These are all actions. That's something that we're doing. Updating a variable is also an action. It's anything that is not a conditional or a loop. We want those to be boxes because we want to know that we're doing something. It's just easier to keep track of it that way. And so we do that, and we want to make sure that we're updating our variables as needed in the code. And you can also see that when I do a while loop, I put it at the end of my process. So when I'm actually coding, I'll actually put while at the beginning, because I'll say while whatever's in the brackets, do those things. But in my flowchart, I want to see the while condition at the end, because you can see it does the steps first, and then it checks if the condition is true, and then if the condition is true, then it goes back up to the first step. And if you have more code after this, you could have a red arrow that goes down and continues it if it's false. But this is basically the kind of format we're looking for, but we're looking for something more complex. So we'll be stitching together loops, we'll be stitching together conditionals and actions to actually get what we want with the sensors. So finally, that brings me to our actual goal for this project. So we've already talked about how we're building this person monitor that can tell how many people are in the room at a given time. So first, we need to create a flowchart algorithm for code that repeatedly reads from these 2 ultrasonic sensors. If one of the sensors is triggered, meaning that the distance is less than 100 first, the number of people in the room should go up by 1. If the other sensor is triggered first, the number of people in the room should go down by 1. This is our directional distinction, and it's what allows us to know if someone is entering the room or exiting. The current count of people in the room should also be sent or outputted to the EEPROM once a minute. It should only happen once a minute, because if it happens more than once a minute, then what happens is our EEPROM gets filled up with data from the first hour of the day, and then you don't have room for the rest of the data for the rest of the day. So you have to space your data so that it's meaningful, and so that you don't take up all 1,000 places for data inside the EEPROM. So in order to only save this data once a minute, we can assume that we can create a clock at the beginning of our code. We just initialize a clock. We just say create clock, and it starts counting in milliseconds in the background while the rest of our code is running. And then every now and then we check how many milliseconds have elapsed, and we say read clock in order to denote that. And if enough milliseconds have passed so that we are at 1 minute, then we would go to saving our data to the EEPROM. In addition to that, we can also read the current distance of the ultrasonic sensor in our algorithm by saying read distance from and then the name of your sensor as you declared it at the beginning of your code. Finally, we can also use the delay function. The delay function pauses your code. It makes everything stop, except for the millisecond clock, because we want that time to be accurate. And so if we had the delay stop the millisecond clock, then this would be a huge issue. Because if we have lots of delays in our code, then these end up stacking up, and then our time count is off. So the delay function stops everything. It stops your sensors from taking data. It stops everything except for the millisecond clock. And this can be very useful, and you'll find out very soon why. So, given all of this, I'd like to get started on the algorithm project, and hopefully we can walk around and help everyone get the algorithm started.